All right, page 455 in your textbooks. Let's take a look at the review, numbers 1 through 4, which we had for homework. Also back on page 292, we did 17. We'll look at that in just a moment. But about the 1 through 4 and 17, 1 through 4 should have been relatively quick and easy. 17, a little bit more work for you there. Bueno.
I have 17.
4, 1, 2, 3, 17. All right. She marches to the tune of a different drummer. All right. Well, let's take a look. Number 1, they gave you a matrix there on page 455, matrix A. They asked for element A2, 2, and what was that, Brandon? 8. How about element A3, 1? Audrey?
1.
A 1. Number 3, if we took double the A matrix and subtracted or added the inverse of the additive inverse specifically of the C matrix, what would our answer be? Abby?
10, 3, 1, 14, 0, 6, 1, 9, 0.
That is correct. 10, 3, 1, 14, 0, 6, 1, 9, 0. And number 4, we had to do 4 times matrix C, 2 times matrix B, and then add those two scalar multiplications together. What did you end up with for your answer there? Genesis on number 4.
4, 8, 22, 24, 10, negative 10, negative 20, 22, 14.
Perfect. 4, 8, 22, 24, 10, negative 10, negative 20, 22, 14. How many perfect on the 1 through 4? All right, so we don't need to see any of these worked out. All right, if you're watching on YouTube and you need help, let me know. I think you're probably good, though, other than maybe a little math error here or there. Page 292, number 17. Let's take another look before we ditch matrices for a good long while. Let's take a look at one more of these systems solved by using an augmented matrix. And what is the augmented matrix we need to start with, Maddie? Number 17.
1, 1, 2, 9, 2, negative 1, negative 1, 0, 1.
Louder. 2, negative 1.
Negative 1, 0.
Another negative 1 and a 0, okay?
And then 1, negative 1, 2, negative 0.
All right. Fact check, make sure this is what I copied. Make sure this is what you said. All right, we're all good? All right. So first things first. The whole desk just collapses. All right, Kendall. First thing we need to make sure of is that we have a
A1 in the A1 spot.
good. In the A11 spot, we have a 1. We got that. All right. Second thing we need to make sure of is that we have, Michael?
Zeros.
Zeros under the main diagonal. So all 3 of these need to become zeros. And thoughts on how we could achieve that, Michael?
You multiply the top by negative 2.
All right, if I multiply a negative 2 by the top, it would give me what for my top row?
Negative 2, negative 2, negative 4, negative 18.
And then I could add that with this row, and that would replace my middle row. So I'm going to keep the 1, 1, 2, 9, but what does that make my middle row become, Michael?
0, negative 3, negative 5, negative 18.
By the way, if they're all negative, I could change them all to positives, for the record, right? I could do that. I don't necessarily have to do that. Audrey, I've got the 0 here. I need a couple more zeros, but this one is my point of emphasis. Now what? Okay, yeah, so just go through the entire top and change all of its signs. Again, just temporarily. I'm going to leave it alone, but temporarily change the signs so that we get
0, negative 2, 0, negative 2.
all right. And now I've got a 0 here, but that doesn't really help. I need a 0 here, and or here's the thought. I like this 0. More zeros is easier, right? What if I flip-flop these 2 rows and worked on getting a 0? No, and it's going to be about the same work anyway. Never mind. All right, so what do we need to do to get a 0 in this spot right here, Brandon?
Multiply the middle by 2 and multiply the bottom by negative 3.
There we go. Or, right, they're all negatives everywhere anyway. I could just go through and change the signs real quick because I didn't really like those signs anyway. So let me just change the signs there and just make it a regular 2 so that my middle row temporarily becomes
6, 10, 32, no, 36.
there we go. Well, technically 0, 6, 10, 36. But yeah, and then the bottom row would become temporarily
0, negative 6, 0, negative 36.
all right, so that I'm going to keep the 1, 1, 2, 9. I'm going to keep the slightly changed 0, 3, 5, 18. but my bottom row becomes the sum, and interestingly enough,
0, 0, 10, 0.
0, 0, 10, 0. And I don't know that we've seen one like this before where you ended with a 0. But what does that mean, Abby?
That it equals 0.
That z, the z value here, has to equal 0. Which means that when we go to solve the y value, we pretty much don't worry about it. That's going to give us a y value of
6.
6. And then Genesis, since I've got a 0 for those z, again, that cancels out. Here we multiply the 1 times 6 to get, but ditch it to the other side as a negative 6. And we essentially just end up with x is equal to 3. And so there's our answer, 3, 6, 0. I saw several people with this answer as I was walking around checking work. How many did have this, first of all? All right, now those who didn't, questions. Again, not that this is the only way to work it, right? There's multiple ways you could work it, but questions on this? Any questions on matrices before we dramatically change gears? All right, well, if you look in your textbooks, you'll notice there's a lot more to matrices that we're not going to cover since we're moving off of Chapter 6. So there is more you could study. I'll let you study that at the college level. Chapter 7, we're going to completely skip it. The highlights of Chapter 7 you'll learn later, mostly during your senior year, okay? But you'll get the highlights of Chapter 7, and frankly, logarithms aren't used a whole lot anyway, so we're going to move off of that. Chapters 8 and 9, we will cover every bit of that your senior year. I don't see an advantage to you knowing it before senior year. It's pretty easy. You'll find it easy your senior year. I'm not worried about that. Chapter 10 is something, if we don't cover it now, we're going to miss out. So Chapter 10 is where we're headed. You can turn to page 450 in your textbooks. So we're going to skip a lot, and we kind of have to skip a lot because we spent a lot longer on stuff this year than the curriculum allowed, but I felt it was better for you to get a thorough education in what I felt was needful than to cover some of these other things that may or may not end up even needing at the college level, frankly. Chapter 10 is all about sequences and series. If you write the term sequence in your notes, sequence. Not sequins, like the shiny little things that if you rub them backwards, they change the way they look. Not those. Sequence. A sequence is an ordered list of numbers. An ordered list of numbers for which a rule determines the next number. A sequence is an ordered list of numbers for which a rule determines the next number. You had these on your COGAT test today. Sequences, where you had a list of numbers, you had to figure out what's the next number in the sequence, right?
We learned this yesterday.
Oh, it's intuitive, though. So the COGAT test isn't designed to test what have you learned. COGAT is intended to see, can you figure it out on your own, like an IQ test. So it's better that we teach it after the COGAT, technically makes it more fair. But anyway, an ordered list of numbers for which a rule determines the next number. Now, every number in a sequence is called a term. Okay, not in the sense of an algebraic term, but it's what we use to describe a number or a value in a sequence. Term refers to a number or a value in a sequence. A number or a value in a sequence. And we said that the sequence has these terms in it, and all of the terms follow a rule to get the next term, right? So the rule is called an algorithm. An algorithm. Really cool sounding word will make you sound smart, right? Algorithm. You probably have heard that term before. How many have heard the word algorithm before? A lot of times you hear it referred to with big tech companies, right? And Facebook uses an algorithm to decide which posts you see, right? Based on who you click like on more and things like that. An algorithm is just a rule that everything else follows. In the case of Facebook, it's with coding, right? In our case, it's going to be with the terms of a sequence. But an algorithm is the rule that the terms follow. An algorithm is the rule that the terms follow. So every sequence has terms. The terms follow a rule. We call the rule an algorithm. Rule is faster to say, but algorithm just really sounds cool. Now, a sequence that has a limited number of terms is called a finite sequence. A finite sequence. It's a sequence with a limited number of terms. A finite sequence. A sequence with a limited number of terms. For instance, if I said I want all the prime numbers from between 1 and 20. This is what we memorized when we were in junior high. I don't know if you would still remember them. If you do, say it with me. 2, 3, 5, 7, 11, 13, 17, 19. Now there's more prime numbers, but you only memorized the ones up to 20, which technically went up to 19, right? Well, if you limit things by saying, okay, we just want the prime numbers between 0 and 20, because really more than that we don't really use that often, that's a finite sequence because you've limited it, okay? But primes themselves go off to infinity, right? There was a proof that proved there are an infinite number of primes. An infinite sequence then, and this, again, term makes sense, I think, an infinite sequence. I'll just abbreviate here. An infinite sequence continues without ending. Right? An infinite sequence continues without ending. For instance, if you wanted to count by, how many remember when you were younger and you practiced counting by fives, maybe in kindergarten, and you realized, like, the teacher usually would stop at like 100, right? The teacher always stopped at 100. Any of you smart alecky little 5-year-olds ever feel like, I could go further though, I could go to 105, 110. Yeah, and then all the other kids in the class were like, shut up. Anyway, but yeah, it's like, hey, it keeps going, and it can keep going and going and going, right? An infinite sequence, right, continues without ending. So for a basic sequence, the key is figure out the algorithm so you can figure out the term that would come next. Again, this is very similar to what you had on your COGAT testing. Now, some terminology for you, some representation. If you see the letter N, N refers to the number of a term. N simply refers to the number of a term. So if you were to see A sub N, this simply refers to any term. A sub N simply refers to any term. If you saw A sub 1, this means the first term. A sub 2, that's the second term. A sub 3, that's the third term. Does that make sense? So how would I represent the 17th term, heaven forbid, in a sequence class? A sub 17, right? If I saw A sub 12, well, that simply means the 12th term, right? That means the 12th term in that sequence. And hopefully we don't go that high with our sequences. All right, look at page 451, some examples here. They give us an algorithm here. A sub n is equal to 2n plus 1. This literally means to find any number term, take the number of the term wherever it falls in the sequence, whatever its number is, double it, and add 1. So the very first term in the sequence would be double the number of the term. Well, its number is class 1. It's the first term. So double the 1 and then add 1 to get 3. A sub 2 means we're going to double the 2 and then add another 1 to get 5. A sub 3 class is going to be, and all of a sudden you're like, I see what we're doing. We're just counting by odd numbers, counting by 3, right? Well, remember, 2x plus 1 is how we represent any odd number, so it makes sense we'd get odd numbers, right, from this particular algorithm. Look at the next sequence. They use the letter B instead of letter A, and that's fine, right? So sequence B, B sub n equals 1 over, is that 2 to the n? Yes, 2 to the n. Well, excuse me, not A, but B sub 1, the very first term, means we're going to have 1 over 2 to the first power, because this is the first term. Well, 2 to the first class, so 1 over 2 to the first. Then the second term is B sub 2. Well, that's going to be 1 over 2 squared, so class, 1/4. Then B sub 3, the third term would end up being 1 over 2 cubed, or 1/8. And so forth. This is right the first 5 terms. So we keep going. We've got a half, we've got a fourth, we've got an eighth. What would the next number be, class? 1/16. You realize we're just basically multiplying by another 2 in the denominator. And the final one would be 1/32. 1/32. That's how we say it correctly. But anyway, and there's our 5 terms, the first 5 terms of the sequence. Does this sequence ever end? No, it could keep going. It could be infinite. We've chosen to limit it to just the first 5 terms, but it could keep going if we so chose. Questions on those examples? Seem pretty easy? Again, the n simply represents the number of the particular term you want, so plug those in. Turn over to page 454. Page 454. I want you to do 1 through 7, the odd. Page 454, numbers 1 through 7, the odd. They give you the algorithm, and they tell you either how many terms they want or which terms specifically they want. Do 1 through 7, the odd, on page 454. Calculators do come in handy in this section, admittedly, so it'd be a good idea to have one of those. Some of you never come to math class without it anyway. Some of you aren't in the habit of using it particularly often, so. Good job, back row. You're front row.
Oh, yeah.
Now we don't actually knock it off with a loud crash. Trigger earthquake. It's true. It's true. All right, let's take a look at these together. Number one of the first 5 terms of the sequence. By the way, when you write a sequence, you generally separate the terms by commas. And so the very first term, of course, is going to be a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, right? So for the first term, what is the n class? 1. So we plug in a 1. 5 times 1 minus 4 gives us 1. Then the next term is term number 2, so the n class is 2. We plug in a 2, we get 6. For the next one, we have a 3 for our n. We plug that in, we get 11. What are we essentially doing here, class? Just adding 5. So what's the next number?
16.
16 and then 21. And in most cases, after you get a few numbers, you kind of figure out the pattern. Just keep it going, right? You don't necessarily have to keep doing the calculations. Not that there's anything wrong with, again, plugging in the 5. 5 times 5, 25 minus 4, okay, that's 21. You could do that, certainly, but in some cases, just kind of figuring out the pattern. How many have these 5 terms for number 1? All right, number 3, it wanted just the 12th term. Now, the wrong way to do this is to start with the first term and keep going until you get to the 12th term. Just find the 12th term, a sub 12, because class, the rule is you take the number of the term and divide by 2. So in this case, class, it's 12 divided by 2 is 6. How many is 6 for the 12th term? Pretty easy. All right, for the next one, it wanted just the 9th term, a sub 9. That's a 9, not a Q. A sub 9. Well, that means we're going to take the number of the term and divide by 1 more than the number of the term. So what is the 9th term going to be, class? 9 tenths. Basically, this would be a series of fractions where the numerator is always 1 bigger. A half, 2/3, 3/4, 5/6, and so forth. But the 9th term would be 9 tenths. Somebody have that for number 5? All right, question? That makes sense now? All right. And then for the last one that you did just now, the 7th term, a sub 7. And again, the algorithm here says add 4 to the number of the term, which in this case is 7, to get 11, and then double it to get 22. How many had 22 as the 7th term in the sequence? All right, question on that. Do we see how this works now? Yeah, probably. Again, it's super easy, right? So, but you understand it now. Excellent. All right, so some sequences are very straightforward, just basic algorithms where you're going to use the number of the term as n to find particular values or sets of values. Another type of sequence you could have is what's called a recursive sequence. Recursive sequence. Re meaning back again, cursive being what you learned in elementary school, so this is, just kidding, it's not cursive writing all over again. Recursive sequence refers to a sequence in which successive terms, a sequence in which successive terms are calculated, long definition. A recursive sequence is a sequence in which a sequence in which successive terms are calculated from similarly constructed previous terms. This may or may not be in your textbook. Is it in your textbook, Abby? Okay. If you're looking to copy it out of your textbook, yeah. There it is. It's on page 451. So you can copy it out of your textbook. I'll be lazy and stand here and watch you write. Recursive sequence is a sequence in which successive terms, that means future terms that come in order, are calculated or found from similarly constructed previous terms. In other words, you need earlier terms to get later terms. And the earlier terms were figured out by doing the same thing you're doing now. Okay, so you just keep doing the same thing, but you keep using earlier terms to get it. Okay, so you use past terms to get future terms. For instance, one example in the book has it in here is called the Fibonacci sequence. How many have heard of Fibonacci numbers, the Fibonacci sequence, golden ratio, golden spiral? Science books. It's in your science books, been in there for patterns in nature, right? But the spiral and different things, nautilus shell, right? Okay, anyway. Well, anyway, Fibonacci numbers basically start with the number 1 and then another number 1. They start with 2 number 1s. And then from there, the next number is the sum of the previous 2. So the next number class would be a 2. Then the next number would be, then, okay, everybody now, not just Brandon. 34, and this pattern just continues on and on and on. It's an infinite sequence. But this is a recursive sequence because you can't just say, I want to find the 7th term and just find it easily because it hinges on previous terms. Does that make sense? It's a recursive sequence. You have to know previous terms to find later terms. Okay, so here's the key. If you put this down under recursive sequence, the initial term, meaning the first term, the initial term must be defined. Sometimes the second term also, like in the Fibonacci sequence, you have to know the first 2 terms to use it. But always in a recursive sequence, the initial term must be defined. They have to specify how the sequence starts, or you really couldn't work it at all. Okay? So a recursive sequence, again, is one in which terms are found or calculated by using previously constructed terms. So a couple of notations here. Whenever you see this notation, a sub n minus 1, we know a sub n means any term, right? For instance, a sub 5 would be the 5th term. A sub 12 would be the 12th term. Well, a sub n minus 1, if 5 is the term you're going for, that would be a sub 4, the one right before it. This notation, you need to know, means previous term. And if you think in that way, if you don't look at this as, oh, a sub n minus 1, if you actually see that and think previous term, it's going to be a lot easier for you. So make sure that's in your notes. A sub n minus 1 refers to a previous term, or the previous term. Look in your books, page 452. Page 452. And they give you a sequence and they give you the algorithm. However, I think my book has it wrong. I'm not sure if your book's been corrected. In the example, is the sequence a sub 1 equals or a sub n equals? Your book says a sub n equals? Okay, so your book is right. Mine was incorrect when they printed it. They fixed it for your book. So the sequence that it should, or the algorithm that they give us is a sub n equals 2 times a sub n minus 1 plus 5. But they have to define a sub 1 as being 3. Does that make sense? All right, now it says they want to find the first 6 terms. Okay, we know the first term, of course, class is 3. I can't just go and find the 6th term. In a recursive sequence, Because it hinges on previous terms, you have to find the whole string of them to get to where you want. So it says find the first 6 terms. It may just be that we want the 6th term, but I need all the terms to get there. What we're going to do for our second term, what does this a sub n minus 1 mean, class? Previous term. So we're going to double the previous and add 5. Make sense? That's how we read this. Double previous term, then add 5. So if we double and add 5, class, 11, double and add 5.
26 or 20.
Double and add 5, 27. Sorry, I was thinking add 3 for some. I'm looking at this 3 and I'm thinking add 3. Okay, now here's where you may need your calculators. Double and add 5. 59. Doubled is 54, add 5, 59. Double and add 5. 123. All right, and then double that and add 5.
51.
And so there's our first 6 terms. But a recursive sequence, again, you can't just say I want the 17th term. You'll be getting the first 17 terms because you can't find term 17 without term 16, which needs to, you get the idea of a recursive sequence. Questions on that? Turn over to page 454. Page 454, where we just were. Let's take a look at number 9 together. Page 454. Let's take a look at number 9 together. Go and write the algorithm down, if you would, please, there in your notes, as well as the starting term. Again, you have to have at least the starting term. Some, like the Fibonacci sequence, you need the first 2 terms. Let's take a look at, scratch that. Let's do number 10. Let's do number 10. Change my notes here. Now, number 10 is interesting because you'll notice it doesn't use what I just pointed out, and that is the a sub n minus 1 means previous term. It uses a sub n minus 2. What do you think that means? The previous term before the previous. 2 terms previous, right? 1 term previous is this. Well, this means go back 2 terms to find the last one. So because they go back 2 terms, you have to know the first 2 terms. They give you a sub 1 and a sub 2. So the first term is 1, next term is 3. And they say they want the first 4 terms. That's not too bad. Well, we already know the first 2, class. The first term is a 1, and the next term is a 3. It says to get any term, go back 2 terms earlier and add 2. So to get this, we go back 2 terms earlier, class, and add 2. Then for the next term, we go 2 terms earlier, add 2. And there we go. So it's a little different, again, that a sub n minus 2, but do we understand it means just 2 terms previous, where n minus 1 literally means the previous. Look at number 12. What's the first 5 terms of a sub n equals 4 plus a sub n minus 1, and they give it a sub 1 is 11. They want the first 5 terms? Go and fill in the first term, obviously. And if we were to translate the algorithm into words, Kendall, what's the algorithm tell us to do?
To add 4.
To the?
Previous.
Add 4 to the previous. So what's the next term going to be, Kendall?
15.
And then Genesis.
19.
And then Maddie. 23, and then Michael.
27.
27. Again, as long as you recognize what a sub n minus 1, or in some cases a sub n minus 2 means, right? Just add 4 to the previous. Okay? The other one was add 2 to 2 previous. Look at number 14. At your seats, find the first 4 terms of that recursive sequence. At your seats, find the first 4 terms of that recursive sequence. Again, you know it's a recursive sequence because you see that previous term notation. If that's in there, it's recursive. And when we translate the algorithm here, basically the algorithm tells us to do what here on number 14?
Add 5.
On number 14?
Yeah. Add 6.
Okay, add 6 to the previous term, right? So it says just the first 4 terms, so my next term is going to be? Well, we're adding 6 to the previous. So as we start with a 6, if we add 6, we get 12. And then the next number,
18.
and then the next number.
22.
Add 6 to 18?
24.
24. And there we go. How many had those 4 numbers? 6, 12, 18, 24. All right, questions on that? Just copied something down wrong or don't know, okay? All right, so number 16 at your seats. Again, finding the first 4 terms of this next recursive sequence. All right, well, Audrey looked at me with eyes that said, please, give me a chance to redeem myself. Okay, actually, she looked at her book the whole time. But I could read between the lines. So, Audrey, the first number is, and we know that because it told us. Right? Now, the rule tells us to do what here, Audrey? There we go. Multiply by 3 and then add 3. So if I multiply by 3 and then add 3, I get 6. If I multiply by 3 and add 3, I get? Okay, so like if we were doing a rapid calculation, 6 times 3 plus 3 equals, yes, 21. And then if we multiply by 3 and then add 3, we get? You said 66, right?
Yeah.
Yes, and that would be correct. How many had 1, 6, 21, 66 for the numbers here? Again, calculators certainly may be used if you want to. Do we feel like we understand recursive sequences? All right, so basic sequences, just figure out the pattern or follow the algorithm to find whatever term they want. In the case of a recursive sequence, you can't find whatever term, you have to find all the terms because everything hinges on the previous initial terms defined for you. I want you to do 2 through 8 the even and 9 to 15 the odd. 2 to 8 the even and 9 through 15 the odd. Let's practice 4 of each type of sequence. And Michael's done already. Show off. Good job, Michael. You may sit there with a smug look on your face, look triumphant as you glare at your sister. Or you can rest your head and look away from her if you feel that's better on your eyes. I'm just kidding, Abby. punishment when a kid was bad, like he was talking to his friends and the teacher was trying to talk. It's like, hide your eyes. I hated that. I got to high school, it's like, man, I need anything to hide my eyes for a few minutes. Brandon's finished. Pretty good, guys. I feel like there's silent trash talking going on, but I could be totally wrong.
You should have us both hide our eyes.
Hide your eyes. There, now you've been told to do it. See? That's not how you hide your eyes, Brandon. Cross your arms on your desk and you lay your head down. That's how you hide your eyes. Maybe it's just my school that did it. Did y'all, when you were little kids, did your teachers ever tell you to hide your eyes? No? Maybe it's just my school. I don't know. Ultimate shame and humiliation. Are you done, Abby?
Yeah.
Okay, Leslie, don't hide your eyes until you're done. That's cheating.
I think we should do this for every problem now.
We should.
Is this finished? Good. Just another minute or so to finish these up, and then we'll take a look at them together. Good, Maddie. Do you want to hide your eyes, Maddie? Heads Up. Do you remember Heads Up 7-Up? Was that a game y'all played when you were
We
little?
played
We were
it
playing
today.
that today.
Really?
In Bible class.
Really? How about that? Interesting. Okay. In Bible class.
It's life management.
We were like doing, Naaman when he came out of the Jordan River.
Yeah.
Okay. Anyway, all right. So let's see how we did. What were the second and the 10th terms? Just those two in the sequence that's described by that algorithm in number 2, Michael.
1 and 97.
Good. The second term is a 1, and the 10th term is a 97. Number 4. What are the first 4 terms of that sequence, Kendall?
5, 7, 9, 11.
Good. 5, 7, 9, 11. Number 6. What are the second and the 4th terms described by that algorithm in number 6? Genesis?
1 and 0.
You're right about the 1, not the 0. Maddie?
1
1 and 2. So as we look at finding a sub 2 for a sub n equals n minus n halves, a sub 4, you found the second term, right? The second term was the 1. For the fourth term, we plug in a 4 minus 4 halves, or 4 minus 2 equals 2. So a sub 2 is, as you said, the 1, and a sub 4 is a 2. Number 8, the third and fourth terms of the sequence described by that algorithm. Let's go back to Genesis for redemption. A sub 3 would have been,
12.
and then a sub 4,
20.
20 is correct. 12 and 20. How many went 4 for 4? You got all 4 of those. All right. Genesis just missed 6, or was there another one we need to see?
6.
Just 6. All right, so we're good to go? Feel like you understand number 6 now? All right, number 10, recursive sequence. Number 9, recursive sequence. Go to the odds now. And what are those first 4 terms if it starts with a 2? Abby?
2, 17, 122, 857.
Yeah, that escalated quickly because you're multiplying the previous term by a 7, then adding 3, so it gets big very quickly. 2, 17, 122, 857. Number 11, the first 3 terms of that sequence by that algorithm there. Brandon?
5, 8, 20.
Good. 5, 8, and 20 are the terms. Again, you're going to take 3 away from the previous and then multiply that by a 4. Number 13, what are the first 3 terms of that recursive sequence? Given that we're starting with a 21. Audrey?
21, 82, 320.
Close.
326.
Yeah, 21, 82, and 326. Not sure if maybe your 0 was written a little funny, or maybe your 6 written a little funny. 21, 82, 326. And number 15, the first 3 terms of the recursive sequence defined by this algorithm, starting with a 20. And let's go back to Audrey for redemption.
20, 10, 20.
Remember, you're dividing by 2. The over 2 means you're dividing each by 2. So you start with a 20, divide by 2 to get 10, divide by 2 again to get 5. So 20, 10, and 5. If we were to have another term, what would it be, class?
2 and a half.
2 1/2 or 5 halves, right? Just keep dividing by 2. But fortunately, they stopped after the third term because then it gets into ugly fractions. Anyone get all of the answers correct on 9 through 15? Got all of those correct. Okay, just missed a couple there. Questions on the 9 through 15? Any questions on any of those? All right. Well, no homework this evening. Might want to study over some terminology here, right? There's a little bit more terminology in this section than maybe we've seen in the past, so keep up with that. But no written homework this evening. Have a wonderful rest of your day. And when the bell rings, you are dismissed.